Hey guys, welcome back. Today we're going to be talking a little bit about math and how it relates to physics and what our expectations are going to be this year for using math in this class. So we've already mentioned how important math is in some previous discussions as it relates to science and specifically physics. As we mentioned, most physicists try to find a simple mathematical formula to relate whatever it is they're studying. These mathematical equations, a lot of times we're going to call them models. They're mathematical models that are going to be representing what we're observing in class and around us in the world. And they also allow us to make predictions. If we can come up with an accurate mathematical model, then we should be able to use that model, that equation, to predict what's going to happen down the line, some later point, or what had happened previously, maybe before we began observing the situation. And so by having an accurate mathematical model, it's actually a very powerful tool for physicists. We can basically predict the future. Now we're going to do some work in class to review, and I'm always available for help. But unless you specifically say something to me, I'm going to assume that you have a fundamental understanding of algebra, that you can manipulate equations, that you know how to isolate variables, that you can do opposite operations to solve for x or y or whatever our particular variable is. That you're comfortable with using squares and square roots, and then from the trig side of it, being able to use sine, cosine, and tangent to find angles and sides, right? Understanding our right triangles. Actually, let's call this C, and that's side A and side B, and knowing at least two of these things, being able to find a third and a fourth and a fifth and a sixth. If after the review we do in class you still aren't sure or you're still struggling, please come in and see me. I'm happy to review with you. I'm happy to go over stuff. If you haven't had any algebra previously and you don't come see me for some extra help, this class is going to be very challenging very quickly. Now, as we work through the math in this and as we develop our equations, we're going to be using a lot of symbols. These symbols are used to represent different variables. And we have traditional symbols that we use. And as you work through, sometimes if you want, it's okay to use your own. But when we're working out problems and solving for things, we're going to try and stick with a common set of variables to represent, a common set of symbols to represent our variables. This way we have a common language. This way anybody in class can look at your equations, look at your work, and be able to follow through and understand what you've done. And there's no question about what each letter stands for. Some examples, lowercase t is our variable that we use for time. A lowercase p, is our symbol for momentum. We'll talk more about why it's a lowercase p in a couple months. The one that might vary a little bit is our displacement or our position. We will sometimes use that lowercase d. We will sometimes use a delta x, a change in x, because we're moving in the x direction or along the x-axis. Or we might say delta y if we're talking about vertical motion, because it's changing in the horizontal direction. We also use symbols for units, and some common ones that we're going to use are lowercase m for meters, lowercase s for seconds. In this case, we also have a superscript 2, so s squared, which stands for seconds squared. And it's important as we go through to keep track or differentiate between our variables our units, and then actually also the one thing I don't have on here that I should is our metric prefixes. Our milli, centi, kilo, hecto, deca, right? Deci. Because these are also important. These are also symbolized using letters. And it's really important not to get the three confused and to also understand that capitalization matters. So, for instance, m as a variable is mass. Lowercase m as a variable is mass. Lowercase m as a unit is meters. And then down here at the bottom, lowercase m at the beginning stands for milli. So lowercase m has a lot of different uses for each of these types of symbol. But then, as we mentioned, capitalization is also significant. Down here we have capital M, lowercase m. That's mega. So capital that's megameter. And so 1 megameter is this. Lowercase m is millimeter, and that's this. So you can see that by making an inaccurate capitalization, we could have a very, very significant difference in our expected outcome or in our calculation. Right? That's a difference of a power of 9. So pay attention to capitalization, pay attention to whether or not you're talking about variables, units, or metric prefixes, and always double check. Along with the letters, because we might have more than one mass in a situation, we might have more than one velocity, we might have multiple values for some given type of variable, momentum, whatever the case may be. And so in order to help differentiate between those, we use subscripts. And subscripts are when they're a little bit smaller and a little bit lower and a little bit to the right. So in this case, we have lowercase v, which is velocity, with a subscript AVE, which stands for average. And so this would be average velocity. The next one we have v sub I, or v subscript I, which would stand for our initial velocity. Okay, what do you think v sub f might stand for? I'll give you a minute to think about it. Hopefully it doesn't take that long. And hopefully you came up with final velocity. Okay. This becomes particularly important when we get into forces, because there are so many different types of forces. And if we just use F for force, we can get lost in all of the different forces involved in a given situation. Then we have our units, and I can't stress enough how important units are. Units give the measurements meaning. Otherwise, they're just numbers. This is such an important statement. This is such an important thing to understand as we go through the year. We're going to measure hundreds of different things. We're going to measure dozens of different variables. We're going to be using so many different numbers that if we can't keep track of what those numbers mean, other than the fact that it's a number, that it's a value, we're going to have a very challenging time. The units are significant. The units are just as important as the actual number or the numerical value of the measurement. They give it meaning. You might say you have 100 of something. What do you have 100 of? Do you have 100 kilograms of feathers? Do you have 100 milligrams of feathers? Do you have 100 grams of feathers? Those are just three massively different, mass, kilograms. It's funny, laugh. These are three massively different amounts of whatever it is, whether it's feathers or tacos or puppies. It doesn't matter, right? So you have to have units. Otherwise, when you go back, when I look at it, when your partners look at it, when your teammates look at it, when somebody outside looks at it, they're not going to have any idea what you're talking about. So use your units. The units that we're going to be using are the units of the SI system, or the metric system. And our fundamental units, our base units from which everything else are derived, are these 7 units. And we'll talk about them all as the year goes on. Some of them we'll use more than others, but hopefully you've seen most of them. Our fundamental unit for distance is meter. Our fundamental unit for mass is the kilogram. Kilogram's interesting, right? Because it's not it has a prefix, right? It's kilogram, not gram. And part of the reason for this is because, at least when, in the early days, a kilogram was a much more useful functional amount of mass rather than a gram. Grams are just too tiny. 1 gram is about the mass of a small paperclip. Seconds for time, units that are called amperes or amps for current. Our SI unit for temperature is Kelvin. Maybe you'll remember that from chemistry, and same thing with the amount of matter. We have our moles. You can have kilomoles. You can have millimoles if you wanted to. And then the last one, and we'll hit on this briefly, but not a whole lot of time on it this year, is a value called luminous intensity, and that is the candela. It's basically how much light over a given area in a given time. But anytime we make calculations, these are the units that our measurements should be in, because these are our fundamental units. If you use kilometers instead of meters, you're going to come up with the wrong value. If you use grams instead of kilograms, you're going to come up with something that's not accurate. So keep that in mind. And then our derived units are all of the other units that are used for anything and everything. They're made up of some combination of those other units. The most common example that we're going to use, the one that we're going to use the most, is probably the Newton, which is our unit for force. And 1 Newton is equivalent to 1 meter times kilograms per second squared. And this superscript -2, if you're not familiar with that, right up here, meters times kilograms times s to the -2. That -2, that's equivalent to meters times kilograms over seconds squared. Okay, so that's all that means. Maybe you can look through some of these other ones, and we don't have to worry about them specifically right now, but we will get through and discuss all of these that are on this page at least over the course of the year, and there are certainly plenty of other units that we'll come across, and many that we won't get to this year. Our metric prefixes are also, hopefully by this point in your science career, you're familiar with the most common ones. And the ones that I would expect you to be pretty closely familiar with are kilo, deci to some extent, centi for sure, and milli for sure. Those 4 are the most common that we're going to come across. But when we get into like waves and things like that, we're going to be talking about micro, nano, and pico, and certainly at the atomic level, those are more common. And then when we get to bigger, you have mega, giga, and tera. Maybe you'll recognize giga when we talk about gigabytes, right? So 1 gigabyte is 1 times 10 to the 9th bytes of data. We're talking about computer systems. And it'll also be important that you can convert between these. You might make a measurement in millimeters, but then have to convert it to meters for calculations, or there are a lot of different situations where I will have to convert. When you were younger, maybe in 8th grade, you were given the metric staircase. That's this delightful little diagram here, where if we're going to larger values, we go up the staircase. And if we're going to smaller values, we go down the staircase. And that's all well and good to have this diagram if you are in 8th grade, but we're not. So I am going to expect that you should be able to convert easily between different metric prefixes and different metric values, whether we're talking about milliliters to decaliters or centigrams to kilograms. Now, as we are making our measurements, using our delightful units with our prefixes, converting in between all of them, and algebraically manipulating equations to solve for variables and make predictions, we have to recognize that our measurements will not be perfect. And we mentioned this in one of the previous lessons, this idea of uncertainty in our measurements. And that no matter how careful we are, due to our inability to be perfect and the level of precision of our instruments, there is going to be some amount of uncertainty and error in everything that we measure, no matter how careful we are. Our job as good scientists is to minimize that uncertainty and that error. So as we go through and we do experiments and we test variables, there are two types of error that we're going to come across. The first is random. And random error, it's not something you can predict. It's, as the name says, it's random. It could be because of environmental conditions. It could be, there's any number of different things that could cause random error. Your buddy walks by when you're trying to take a measurement and smacks you in the back of the head. Whatever it happens to be. These, though, are not mistakes on the part of the individual, and that's important as we analyze data and talk about our results and talk about our error. When you were in previous classes, you might have done an error analysis and talked about misreading the scale or miscalculating something. Misreading, miscalculating, incorrectly using instruments, those are not random errors. Those are mistakes, and those shouldn't happen. If you misread, then you go back and reread. If you miscalculate, then you go back and you recalculate. Those are not things that should be left within your write-up, within your data. They should be redone. If you make a mistake, fix it. Sometimes, though, you have errors, you have things that occur that are beyond your control, and those are our random errors. So make sure you understand the distinction between random error and mistakes. I don't want to read about the mistakes that you made in your lab. I want to read about the errors and how you can address them and make them fewer in the future. The second type is systemic or systematic. Slightly different words, they mean the same thing. And this is something that affects the entire data set in the same way. A really good example is if you're finding the mass of a set of things, a set of objects, and you don't zero the balance out. You don't zero the electronic balance out. And so it's off by 0.2. When you make your measurements, every single thing that you're going to find the mass of is going to be off by 0.2. And so the relationship that you observe between the variables, whether it's size and mass or whatever it happens to be, is going to remain the same. Something like the slope of your line isn't going to be changed by a systematic error, but it's going to offset your data. It's going to raise it up the y-axis, or it's going to drop it down the y-axis. Sometimes these are called zero offset errors, because if you're doing something that you're measuring a proportional relationship that should go through the origin and you have a systematic error, it's going to offset it from zero where it should be. These, again, they're not always controllable, but we should certainly pay attention to what we're doing and pay attention to our equipment and try and minimize the systematic errors within an experiment. Within this idea of uncertainty and error, two additional ideas that we should understand are precision and accuracy. Precision is how precisely, there you go, you can actually make a measurement. And this has a lot to do with the device that you're using. The better devices, the more precise your values can be, and actually the more accurate as well. But when we talk about precision, it's very low in random error. So what that means is that, and the best example, and the example that you'll see a lot is shooting arrows at a target. And if we have a target, and let's say you shoot 5 arrows, 2, 3, 4, 5, and this is their spread pattern. That's a fairly precise set of shots. However, if we have something like this, 3, 4, that is not very precise. Now, one of those was very accurate, right on the bullseye, dead in the middle, but not very precise because they're all over the place. And so you can see there's a big difference between each individual measurement, meaning there's probably a lot of random error within your experiment. This here, if that was a set of data, that would indicate very low random error, but you can see that it's fairly inaccurate. And so that would indicate some type of systematic error. And so maybe if you're shooting bows and arrows, the sight for your bow is off by a little bit. So it's causing you, every time you aim for the bullseye, you end up shooting it to the upper right slightly. Then the other term is accuracy. And this is how close your measurement is to the actual value or the accepted value. Now, we don't always have an accepted value, but when we have an accepted value, we can compare it and see how accurate we are. Accurate experiments, accurate measurements have fairly low systematic error. Now, when we're calculating, let's see if we can do this. When we're calculating, if we have a known value, we're going to compare, we're going to assess our error using a percent, we call it percent error. And the percent error is the accepted, actually the absolute value of the accepted minus the measured. These lines here mean absolute, so if it's a negative, we just ignore the negative sign. So the difference between the accepted and the measured divided by the accepted value, and because we're going to do it as a percent, it's going to be times 100. So that's going to give us the percent error in our experiment. So that's with a known value or accepted value. Then with no known, typically here when we're looking and we have no known value, we're going to measure the same thing from multiple approaches. So we might measure inertial mass and gravitational mass, and those are terms we'll talk about later in the year. And so for no known value, where we have two different measurements from two different ways, we're going to find what's called the percent difference. And percent difference is the absolute value of the difference of the two numbers divided by the average times 100. And I'll have some examples of these in class to work through when we get to class next time, so that you can get a better idea of how to calculate these and understand what we have going on. But those are the two approaches that we have. Then as we make measurements and make calculations, if you took chemistry, they're pretty hardcore about sig figs. A little bit less concerned about sig figs, although we should certainly have a sense of them and sense of what they are. In any case, the significant digits of a measurement should be the number that are known with certainty plus the first uncertain digit. So if we have a ruler that has centimeters And so if each one of these is 1 centimeter, then when we measure it, when we measure an object, let's say this is our object. So that's 1, 2, 3, 4. It's somewhere between 4 and 5 centimeters. Clearly not 4, clearly not 5. So we're going to estimate that it's about 4.5 centimeters. That gives us a little bit more precision in our reading. If it's right dead on, a 4 or a 5, then we do 5.0 centimeters. You still include that first uncertain digit, that first estimated number, but make it a 0 if it's right on the line. When we calculate, when we carry significant figures through our calculations, our significant figures should always go to whatever the least number of significant figures is. If you have one measurement that is 5 and then you have another measurement that's 3.467, the most precise, the most significant figures that your value can have is 1. Because the lowest amount of significant figures dictates the final value. Now, for our purposes, typically when you're calculating and things like that, and we're not worried about measurements, we go to 2 decimals. So say 1.57. 2 decimals is a good number of places to go. It gives us a fairly accurate value, and we can go from there. Then we have our uncertainty. And again, this is related to the actual device itself. And again, this is, we talk about like a ruler that has centimeter graduations or centimeter divisions. 1, 2, 3, 4, 5, 6, and those are centimeters. Okay, so the smallest graduation is 1 centimeter. When we're talking about the uncertainty in our measurements, for an analog device, the uncertainty is always half the limit of the division. So in this case, it's 1 centimeter, which means if we measured our blue bar again here, that is 4.5, but it's not, it might be off a little bit. There's about a half centimeter uncertainty in there. So we say plus or minus 0.5 centimeters. So this is what our measurement should look like. What this means is that we can say with almost 100% certainty that the actual measurement of that blue bar is somewhere between 4 and 5 centimeters, right? And this is a fairly straightforward example, but you can see that that's pretty clear. If we have smaller error bars, then we can have smaller, or if we have smaller divisions, then we have smaller uncertainty. And that's always a good thing. With our uncertainty, we have 2 different types. We have what we call our absolute uncertainty. This is like what we just looked at. It has a magnitude and a unit. We get it from the device. We get it from the measuring tool. So an example would be 0.001 meters. This is, so we have milli, so our measuring device here must be 2 millimeters to have a plus or minus 0.001 meters as our uncertainty. Then we have what's called relative or percent uncertainty or error. And this is the value, the absolute uncertainty, divided by the measurement. So if we refer back to that previous measurement where we have 0.5 is our uncertainty divided by 4.5, which is our actual measurements. Right, let's take a minute and calculate that, see what we get. And what did you get? Great. This becomes important when we're carrying error and uncertainty through calculations. And again, these are things that I'm going to hit on again in class, but I want you to at least see it. We're going to have some practice problems with this as well. So don't get too worried if you don't fully understand, but make some notes, keep track of what you're not sure about. When we are adding or subtracting measurements, so say 5 meters plus 5 meters, we're going to add the absolute error. So if it's 5 meter, actually let's do this. 5 plus or minus 0.5 meters plus 5 plus or minus 0.5 meters. Okay, so what we're doing is adding two 5-meter measurements. Each one has an uncertainty of 0.5 meters. So our final answer here, is 10 meters plus or minus 1 meter, because we added the two absolute uncertainties. So 0.5 plus 0.5 gives us plus or minus 1 meter. If we're multiplying or dividing, then we're going to add the percent errors. So same idea, except we would have that extra step of what we did up here with the 0.5 over 4.5. We have to convert to a percent error, and then we add the percent errors, and that would be our final error. And again, we'll do some practice problems with this, but it would be like 5 meters plus or minus 1%. And so then we would, if we were multiplying those together, so 5 times 5 plus or minus 1%, then our final value here would be 25 meters plus or minus 2%. When we're creating graphs, and we'll be creating many graphs this year, graphs are a great way to show our data, to show our relationships. We're going to use error bars to indicate our uncertainty. And we'll talk about how to do that using Logger Pro. But on our graphs, our error bars will look like this. And that tells us the uncertainty in our in each data point. As a general rule, our lines of fit should pass through all the error bars. And if a best line of fit, if there's a piece of data that doesn't meet that criteria, so you draw your fit line and there's a data point whose error bars don't cross our fit line, then that is a great indicator that it's an outlier. And this is a really good graphical representation, a good way to identify outliers, and then you can discuss them, maybe go back and remeasure, double check your work, see what's going on there. A couple other things here to discuss, some types of measurements, and then we'll talk about some trig. So we have two different types of measurements that we're going to be using this year. The first is scalar quantities, and these might be what you typically think of as measurements. They are quantities that have just the value and the unit. So we have some examples here: 50 kilograms, 6 volts, 1200 candelas. The units and the magnitude completely describe the measurement. Things like mass and electrical current are scalars. Now, that's different from our vectors, because our vectors have the additional piece of information that is direction. Okay, so they have direction. Vectors have direction. And so it's not enough to just give the magnitude and the unit. It has to also have a direction. So you might say there's a force of 20 newtons east. There is an object moving or accelerating 5 meters per second north. if we're working in one dimension, a simple left or right is sufficient. And this is important because, and again, something we're going to get more into, when we add, subtract, multiply vectors, it's a little bit different than just adding normal numbers. We can't just add them and subtract them. We have to pay attention to those directions and how they affect the vector. Okay, really quickly, when they're parallel, when they're in the same direction, we can add them just together. When they're parallel but in opposite directions, they're subtracted. And then if they're not parallel, so let's say we have something like this and something like that, and those are our two vectors, then we have to use our trig. And so here's where our sine, cosine, tangent come in. Again, as I mentioned, you should be comfortable using sine, cosine, and tangent. We will use them a lot this year. You should be comfortable using Pythagorean theorem. So the big ones are going to be Pythagorean theorem. And also, really, it's law of sines. But understanding SOHCAHTOA. And then you don't necessarily need to understand that this is law of cosines. We're going to talk about breaking vectors up into components and adding vectors using components, but there will be some situations here where being able to use the law of cosines might be helpful. Not something you specifically need to be able to use, because we will talk a lot about breaking vectors up into components and adding them that way. But if you understand it, if you're familiar with law of cosines, that'll be something that's useful. Okay, I know that was a lot. Hopefully you broke it up a little bit. Go back and review the things that you might have trouble with. Make sure you've written down questions to ask me when we see each other again. I will see you soon.